Okay, so our next application of trig is in the area of vectors. In this application, it is another place where we need two numbers. It requires two numbers to describe what a vector is. A vector, and some of you may have had this in physics already, but a vector is made up of something called its magnitude and its direction. Now, geometrically, we can demonstrate a vector as it kind of looks like a ray, but from geometry. However, it is different than a ray. We do have an initial point, and then the arrow, which shows direction. The length of the vector is what we will call its magnitude. And as you can see, the arrow is showing a certain direction. So I could have all sorts of different vectors going in all sorts of different directions. Traditionally, we name a vector with a bold lowercase letter. Something like this. Oftentimes, we will also name it, if I have a point P to a point Q, let's say, I could name this as vector PQ, and when we're looking at its length or its magnitude, what we really want is the distance of that segment, and it will be denoted something like this quite often. So just some symbols in your book and how you might recognize a vector. Now, any vector that has the same magnitude and same direction, we say are equivalent. So for example, if I had this vector and this vector, although they are in different locations, they are equivalent vectors. Because their magnitude is the same and their direction is the same. Now, this is kind of the geometric representation of a vector. Now let's look at a little bit of the algebra for the vector. And it's probably easiest if we just take an example. If I had, an example from algebra, and we'll say we have a point P, let P be the point 1, 2. We're going to put this on the coordinate plane so we can talk about it a little easier. The point Q at 5, 4. And I want to find the magnitude of vector PQ. Okay, so let's graphically look and see what we've got going on. So we have the point 1, 2, and we have the point 5, 4. This is our vector. And if we want to find its magnitude, basically what we're asking to do is find its distance. In order to do this, this is where we're going to apply a little bit of trig, or in other words, Pythagorean theorem, because what we can do is make a right triangle out of this. We can very easily find this distance across here, and we can very easily find the horizontal and vertical distance, this distance across here. And if we know those things, then we can do a squared plus b squared equals c squared. Technically what we're doing is we are using our distance formula. If you remember your distance formula. So we have our x values, 5 minus 1 squared, plus 4 minus 2 squared, and we'll take the square root of that. So we have 4 squared plus 2 squared in our radical, which is the square root of 20. And we can simplify that. That's 4 times 5. So 2 square root of 5 is my distance here. Now, very simply, geometrically, we could have even counted and found that this distance is 4 and this distance is 2 and just done a squared plus b squared equals c squared. Geometric representation of it, algebraic representation of it. So our magnitude for vector PQ is 2 square root of 5. We can find our magnitudes. Any vector that has this magnitude potentially could be equivalent to this. The other piece of this, though, other than just the magnitude, is that we have to be going in the same direction. So in order to decide whether they're in the same direction, algebraically what we would have to do, well, we could do it a couple of ways, but algebraically it would be easier to look at the slope. Trigonometrically, we could look at its angle to the horizontal. But to start with, since we said this was an algebra example, let's just look at the slope. We would find the slope of this line. The slope of PQ, remember, is our change in y over our change in x. So in this case, our slope, rise over run, 2 over 4, in other words, is 1/2. So anything that had a slope of 1/2 and a distance of 2 square root of 5 would be an equivalent vector.